Good morning, students. In last lecture we have discussed about the congruence relation. Okay. Now in this lecture we are going to discuss the quotient semigroup or we can say factor semigroup. So first of all, the construction of quotient semigroup. So we have considered this theorem. There are some explanation in between this theorem. Okay. So first of all, the theorem is let A star be a semigroup and let R be a congruence relation defined on A star. Okay. What is, we have given one semigroup and congruence relation R on that semigroup. Okay. Now every congruence relation is an equivalence relation. So here R is an equivalence relation on semigroup S. Okay. So now for any element A belongs to S, the equivalence class containing A is given by equivalence class of A is equal to set of all B belongs to S such where B is related to A, or we can say A is related to B because our R is an equivalence relation, so it is symmetry. Okay. So for this equivalence relation R, we have considered the equivalence class of particular element A. Okay. Now it is known that an equivalence relation R on set S partitions set S into equivalence classes. You can verify this result in Google. Okay. How it is possible? If we consider any equivalence relation on a particular set, then the equivalence classes of this under this relation partition the given set S into, okay. इसका मतलब क्या होगा, जो हमारा सेट S है उसका पार्टीशन हमको मिलेगा. पार्टीशन क्या होता है? कलेक्शन ऑफ डिसजॉइंट सबसेट होता है, और उस डिसजॉइंट सबसेट का जब हम यूनियन करते हैं तो हमारा सेट S मिलता है. Okay, partition is the collection of disjoint subset of S and the union of all these subsets is equal to given set S. Okay, so अगर हम इक्विवेलेंस क्लासेस का कलेक्शन कंसीडर करते हैं तो वो हमारा सेट S है उसका पार्टीशन क्रिएट करेगा. आगे देखते हैं. Let S quotient R denote the set of all equivalence classes determined by R. Okay. We denote this is the collection of all equivalence classes determined by the equivalence relation R. Okay. Now we define binary operation star on S quotient R as follows. Where this is not star but this is ring star. Okay. We can say this is ring sum, so this is ring star. We define binary operation ring star on S quotient R as follows. Ring star is a map from this binary operations. Our set is S quotient R. Okay, so ring star is a map from S quotient R cross S quotient R to S quotient R. Okay. Now the element of here it is S quotient R. We consider the order pair of equivalence class of A and equivalence class of B from S quotient R to S quotient R, and the ring star is defined as equivalence class of A star equivalence class of B is equal to equivalence class of A star B. This is the ring star binary operation and this is the binary operation for our semigroup S. Okay. Or we can also denote it by ring star into order pair equivalence class of A and equivalence class of B. Okay. Then S quotient R forms semigroup under this binary operation ring star. Okay. This is our theorem. What is our theorem? If we consider congruence relation on semigroup S star and S quotient star is collection of all equivalence classes determined by R, then under this binary operation ring star S quotient R forms semigroup. This is our theorem. Now the proof of our theorem, or this is theorem, or you can say this is the construction of our quotient semigroup or a factor semigroup. Okay, let us see. Now here we have defined ring binary operation ring star. So this is the map. Okay. So first of all we saw that this binary operation is well defined. Okay. For that we have considered two element. Okay, two order pair from S cross S quotient R cross S quotient R, and both are equal. So consider order pair of equivalence class of A and B is equal to order pair of equivalence class of A dash and B dash. Okay. From this we can say that A is equal to equivalence class of A is equal to equivalence class of A dash, and similarly equivalence class of B is equal to equivalence class of B dash. Now the equivalence class of A and A dash are same. So then it is known that A is related to A dash. Okay. If for two element equivalence classes are same, then they both element are related with each other. Okay, by equivalence relation. So here equivalence class of A is equal to A dash. So A is related to A dash, and similarly B is related to B dash. Okay, from this. Now from this our R is a congruence relation on semigroup S star. Okay. So A is related to A dash and B is related to B dash. So A star B is related to A dash star B dash. Okay, what do we get? A star B is related to A dash star B dash. Okay, so here we get relation A star B related to A dash star B dash. Now this element and this element are related by relation. Okay, so equivalence class of both these element are same. So equivalence class of A star B is equal to equivalence class of A dash star B dash. Okay. So again by the definition of ring star we get equivalence class of A star equivalence class of B is equal to equivalence class of A dash star ring star equivalence class of B dash. Okay. So here we have considered two elements of domain are same. So we get the images of these two elements are also same. Okay, whenever we consider two elements are same, then their images are also same. Okay, this is the definition of function. Every element has a unique image. Okay, if every element related with the unique element of codomain. Okay, so by this way we can say that star is well defined binary operation on S quotient R. Okay, now our aim is to show that S quotient R is semigroup under this binary operation ring star. Okay, so to show semigroup first we show that ring star is an associative binary operation. So let us see. Let equivalence class of A, equivalence class of B and equivalence class of C is belongs to S quotient star. We have considered three elements from S quotient R. Okay. Now equivalence class of A ring star, equivalence class of B ring star, equivalence class of C. Then this is equal to equivalence class of A star ring star. Now apply the binary operation on this B star C. Okay, now again from this step what we get? Equivalence class of A star B star C. Now star, S star is a semigroup, so star is associative binary operation. So what we get? A star B star C from this step. Okay, what this step is obtained because star is associative. Now again what we get? Equivalence class of A star B, this will become ring star, and equivalence class of C. So finally what we get? Equivalence class of A ring star, equivalence class of B ring star, equivalence class of C. Okay, by this way we can say that star is associative binary operation. Okay, so star is ring star is well defined and ring star is associative binary operation. So S quotient R with binary operation ring star is semigroup. Okay, and this semigroup is called quotient semigroup, or we can say factor semigroup. So this is the construction of quotient semigroup or factor semigroup. For that we have defined S quotient R as the collection of all equivalence classes under the relation R, and we have defined the new binary operation ring star on this set S quotient R. Now there is a note here. Star is a type of quotient binary relation. Okay, star is the type of quotient binary relation on S quotient R that is constructed from the original binary relation star on S. Okay, in how we define the ring star? The ring star is defined as the equivalence class of product of element. Okay, under this relation star. Okay, how we have defined? Equivalence class of B star C is equal to equivalence class of B star C. Okay, so here we use the our original binary operation star. Okay, so here we can write that ring star is the type of quotient binary relation on S quotient star S quotient R that is constructed from the original binary relation star on set S. Okay, by the congruence relation. Okay, also these equivalence classes are obtained from the congruence relation R. Okay, so in the construction of semigroup, what we have considered? We have considered our main binary operation star. Okay, then after the congruence relation R. Okay, from both this property we have constructed, by using this property we have constructed binary operation ring star. Okay, so this is a note. Now corollary 1 for this above theorem. Okay, let R be a congruence relation on the monoid S star. Here we have in last first theorem S star is a semigroup, but here it is monoid. R is the congruence relation on the monoid S star with identity E. Okay, if we define binary operation ring star in S quotient R, this is the same definition as we defined above. Okay, for all, then S quotient R with ring star is a monoid. Okay, what is given? We have given one monoid S star. Okay, and congruence relation, and we define the binary operation ring star on S quotient R. Then what is our aim? Our aim is to show that S quotient R with ring star is also monoid. Okay, so from our previous theorem, in last theorem, it is clear that S quotient R with binary operation ring star is semigroup. We have just proved this. Okay, S quotient R with binary operation ring star is semigroup. Now it is enough to show that S quotient R has a identity element. So it is enough to show that equivalence class of E is identity element for S quotient R. Okay, so let us see. Let any arbitrary equivalence class of A belongs to S quotient R and equivalence class of E belongs to S quotient R. Now equivalence class of A ring star equivalence class of E is equal to equivalence class of A star E. This is equal to equivalence class of A. And similarly you can see that equivalence class of E ring star equivalence class of A is equal to equivalence class of E star A. E is the identity element, so what we get? Equivalence class of A. Okay, so from both of this step we can say that equivalence class of E is the identity element for S quotient R. Okay, so for this semigroup what we get? S quotient R is a semigroup with identity element is equal to equivalence class of E. Okay, so S quotient R with binary operation ring star is a monoid. Now this is a very simple corollary. Now the corollary number 2. Let S star be a semigroup and R is a congruence relation on S star. If S star is a commutative, then S quotient R with ring star is also commutative. In corollary 1, S star is monoid, so then after we saw that S quotient R is also monoid. And in this case, S star is commutative. So now we saw that S quotient R is also commutative. So let us see. let two elements equivalence class of A and B belongs to S quotient R. Now what is our aim? Our aim is to show that binary operation ring star is commutative. So equivalence class of A ring star equivalence class of B is equal to equivalence class of A star B. Now our star is a commutative binary operation. So A star B can be written as B star A. So equivalence class of A star B is equal to equivalence class of B star A. Okay. So equivalence class of A star B is equal to, from this equivalence class of A ring star B is equal to equivalence class of B ring star equivalence class of A, from this step. Okay. So from this we can say that our ring star is a commutative binary operation. So S quotient R with binary operation ring star is a commutative. Now next theorem is, let R be a congruence relation on a semigroup S star, and let S quotient R with ring star be the corresponding quotient semigroup. Okay, we have given congruence relation semigroup S star and quotient semigroup S quotient R. Okay, then the function fr from S to S quotient are defined by FRA is equal to FR of A is equal to equivalence class of A is an onto homomorphism called the natural homomorphism. Okay, this homomorphism is called the natural homomorphism. So what we have given? We have given one congruence relation on semigroup S star. From this we have constructed quotient semigroup S quotient R with binary operation ring star, and the function is the from S to S quotient R defined as FR of A is equal to equivalence class of A. And now we want to show that this is homomorphism and also onto homomorphism. So first of all we saw that this function is onto. Okay. So for whenever we consider any equivalence class of A belongs to S quotient R, okay, whenever we consider equivalence class containing element A belongs to S quotient R, and what we get? We get element A. This belongs to S quotient R, and A is the element of S. Okay, this is the equivalence class of element of S. So for this element equivalence class of A, we get element A belongs to S such that FR of A is equal to equivalence class of A. ओके, किसी भी एलिमेंट के लिए हमको S में से एक एलिमेंट ऐसा मिल जाएगा जिसकी वजह से FR of A is equal to equivalence class of A. Okay, so our map FR is an onto function. Okay, now what is next? Next is, now we saw that this is homomorphism. For that, consider two element A, B belongs to S and apply the function on product of these two elements under the relation star. So FR of A star B is equal to, by the definition, equivalence class of A star B. This is equal to equivalence class of A ring star equivalence class of B. Now equivalence class of A is equal to FR of A ring star FR of B. So here this is the binary operation of domain. Here we get binary operation of codomain. So from this simplification we can say that our function FR is a homomorphism, and from previous discussion we can say that function FR is also onto. So this natural homomorphism is an onto homomorphism. Okay, we use this homomorphism in the fundamental theorem of homomorphism, which is we are going to discuss in the next lecture. Okay, so these are some basic information about the quotient semigroup, and some we have discussed some corollaries about this quotient semigroup. In next lecture we have discussed in upcoming lectures we have discussed fundamental theorem of homomorphism, as well as we will also discuss some examples of this quotient semigroup. Okay, so this is enough for this lecture. We will continue in the next lecture. Thank you.